Righty, there we go. All right, so again, I said that the second one might not make logical sense because I didn't have enough time to think about it, but anyway. So let P of x be x is prime and Q of xy be x is slower than y. Why is that thing in the way? Determine the true false values of the following. P of 7 is 7 prime. Yes, it is. So since 7 is prime, this first one would be true. P of 16 is 16 prime. No, it's not. False. Q of cat is slower than turtle. In general, are cats slower than turtles? No. I can tell you from experience, I have both a cat and a turtle. Actually, the turtle's pretty speedy when he wants to be. But anyway, we're going to go with the normal slow turtle idea. And then, oh, you couldn't hear? You can't hear now. Hooray! And then Q slug dog is slug slower than a dog? Yeah. In terms of the exam being online, if you're physically able to be here, you're not in quarantine, you're not isolated, unfortunately, I'm expecting you to be here. Sorry. All right, question on that one? Okay, I'm not sitting down to be rude. I'm sitting down so people over there can see. So given h of x means x is hungry, b of x means x is a bear, and e of xy means x will eat y, interpret the following if x and y are all mammals. And again, this is the one that might not make sense. I don't really know. I haven't written it down yet. So if we go from left to right, we'd have for all mammals, bears are mammals, right? X, there exists. I'm just realizing that bears are mammals, right? Okay. I'm a math person and a math person alone. Anyway, so for all mammals X, there exists a mammal Y such that we do have an implication, so we're going to have an if in there. So if X is hungry and X eats Y, or X will eat Y if I want to be particularly careful, then Y is a bear. I don't think that makes much sense, but it could just be a false statement. These never have to be completely true, but that's how that would go. If you wanted to try to write that in better English, you could go right ahead. I'm not going to take the time to try to do it. As always, I don't mind if you write the literal as opposed to kind of everyday English. The one last thing I'll remind you, which is, again, something that I didn't have on here, but will be on your quiz, is the counterexample idea. So just to touch on it super quick, remember you kind of have two options. You might want to show that a counterexample for this type of idea. So if you want a counterexample for this, you need one value that makes P of x false. That's kind of the more intuitive way, but then we also have wanting to give a counterexample for this, an implication. And remember, to do that, what you want is you want one value True story accidentally muted. Sorry about that. Okay. So yeah, counterexamples. You just have one thing, make it false. Implication, make the beginning thing, the hypothesis true, and the conclusion false. Sorry about that. I don't know. I must have just hit that by accident. Questions, concerns on the warm-up while I pull up our notes that I didn't have pulled up yet because I'm apparently not ready. So we're gonna go through the rest of as much of 1.5. Can we do a counter example? No, because I can't think of one, but let me try to pull one up really quick. Trying to think of those off the top of your head is never going to be a good idea.
Something with a statement that's clearly false would be pretty easy.
I guess maybe. Let me think. Well, I think they want one for the implication piece. So let's say, oh, but you literally just did it. So yes, when they actually are time to take the quiz, it will be on Blackboard under the assignments tab, yes. So let's say if X is a number between, this one might seem super dumb, but it gets the point across. Not that your example was dumb. If X is a number between 0 and 10, then X is even. So we have an implication here. So we'd essentially want to make sure that the beginning is true. It's a number between 0 and 10, but the end result is false. So we'd want it to be an odd number. Well, what's a number that makes that happen? 1, 3, 5, 7, 9. Pick one. 7 is between 0 and 10, but is odd. So you wouldn't want to say 11 because 11 is outside of 0 to 10, and we want to make sure that that beginning statement is true, but that end statement is the thing that you want to make sure is false. So that seems like a little wishy-washy of one, but finding the good ones are hard. Anyway, gotta pull this up. Why was I not ready? Because I'm bad at this. I kind of hope we finish 1.5 today. We'll see what happens. And I've got to actually get it to you guys. So just a quick breeze through what we had been talking about. So we've been talking about methods of proof. And one thing that you got to have to remember to use in this section is we use a lot of the definitions from 1.4. So the definition of even, the definition of divides, the definition of odd, that kind of jazz. So we started talking about direct proofs, which was an idea that we start with the hypothesis and we state a bunch of different true things that lead us to the conclusion. There are some different ways that we can do proofs as well. So that's what we're going to talk about today. The first one being something called proof by contraposition. We know what the contraposition is. Contrapositive contraposition. Yeah, that's how that works. So recall from 1.1, the contrapositive of a implication P implies Q is, I always forget to actually allow myself to draw, is not Q implies not P. Also remember that the statement, the original statement, and the contrapositive are logically equivalent. you could essentially replace one with the other and it still gets the same point across. They have the same true-false values. So therefore, if it's actually easier to prove not Q implies not P, then we can conclude the original statement as well, because if not P implies not Q is true, then P implies Q must be true. So sometimes it's going to be easier to kind of prove the opposite, if you will, and we can do that and still get the original statement proved as well. So let's see how that'll work. So I'm going to leave that there. So say I wanted to prove the following. Let n be an integer, and I will say on exams, I'll specify prove by contraposition, prove. Maybe I won't say prove directly, but if it doesn't say prove in some other way, you can assume it'll be proved directly. But there's proof by contraposition. There's also proof by contradiction, which we'll get to in a second. And with contraposition and contradiction, I will specifically state those as proof by contraposition, proof by contradiction, so that you don't have to sit there for 5 hours and think about which way it might work. So prove the following. Let n be an integer. If n squared is even, then n is even. So the first thing I might think about is, holy cow, how the heck do I prove that like the square root of something is even? That sounds like a bad idea. But if we think about the contraposition, the contrapositive here, so the contrapositive is, so not Q, so if Q is n is even, then we'd have n is odd, implies n squared is odd. And going from the quote-unquote smaller value to the larger value seems like it might be an easier thing to prove than trying to like undo the squared. So this is probably going to be easier to prove. So let's try to prove this. Now we're going to prove this directly. So we find the contraposition, but then do a direct proof on the contrapositive. So remember, direct proofs, we start with saying what we have. So what we have is that n is an integer that's odd. So we're going to say let n be an odd integer. And then you kind of always state what we're going for. What we're going for is we want to show n squared is odd. And this is usually where, personally, I'll pop off to the side and kind of do my scratch work to make sure I know how my proof wants to go. So let me see what I have. Well, what I have is that n is odd. Well, if I use the definition of odd, that means there's some integer k that I can write it like 2k plus 1. So let me find what n squared would be in that case and see if I can somehow manipulate it to look like it's an odd integer. So n squared would of course be 2k plus 1 all squared. Let me scroll down a little bit. I think most people will have that written out now. So if I FOIL that out, we'd get 4k squared plus 2k plus 2k plus 1. Well, now the goal, which I'll kind of write down here, would be to have it as 2 times something plus 1, because I want it to be odd. Is there somehow that I can manipulate what I have to look like that? And we kind of did one that's similar to this the other day, where we had the same kind of idea, and then we plopped it into the odd format. So we have the plus 1, so let me not move that. But if I look at the rest of it, I have 4k, and let me kind of, that circle is now starting to leak into some stuff. So we have 4k squared plus 2k plus 2k. All of those things have a 2 in it, so I can factor it out. So if I factor out that 2 from all of those first 3 pieces, I'd be left with 2k squared plus k, and I didn't touch the plus 1, so that wasn't part of the factoring. You can combine those 2 k's to get 2k, of course, which I'll do right here, because I don't have enough space. So what I've I've just done is I've taken my odd integer, I've squared it, and I manipulated what I had into what I wanted. And now I know that my proof's going to fall out exactly from those steps. Does that make sense? Now, again, if you're getting super good at these and you don't want to do the scratch work off to the side, because if you think about it, this just kind of fell out if you just started doing it. If you just want to start writing it, but that's not always going to happen. Sometimes you have to go on a wrong track to get where you're going. But so if we start writing this out formally, we'd say since n is odd, there is an integer k such that n equals 2k plus 1. And then essentially just show them the work you just did off to the side. So n squared is 2k plus 1 all squared. 4k squared plus 2k plus 1. We can factor that out, make that 2k squared. I'm going to write plus 2k. So I combine those two together to get 4k, and then when I factor it out, I just am left with 2k. Now, the one last thing we have to say is that to be an odd integer, the thing that you're multiplying the 2 by has to be an integer. But again, by that axiom 1 that we went over the other day, that is an integer. It's just integers multiplied together and added together at other integers. So since 2k squared plus 2k is an integer, n squared is odd. I guess that's technically the conclusion of the direct proof part, so I should make that step 4. The one tiny last extra step you have to take here is you then have to just state that because of the fact that we just proved the contrapositive, we've now proven the original as well. So kind of this extra step that we pick up for these contrapositive proofs, therefore, by contraposition, if n squared is even, then n is even. Does that make sense? Going once, going twice. Questions, concerns? Okay. The big thing with these is just manipulating definitions. So you really going to need to remember and know those definitions, because whenever I say something is odd, you're going to have to remember, well, I can write that as 2k plus 1. That's like the meat and potatoes of these, is remembering the definitions and just kind of manipulating them a little bit with some math. I think these are fun, but people think I'm nuts, so anyway, moving on. I'll try to leave the last couple lines in there just in case. Prove the following. Again, on a quiz or an exam, I would say by contraposition. Let n be an integer. If n squared minus 6n plus 5 is even, then n is odd. So kind of a little tip off for contraposition if, say, WebAssign doesn't let you know. If you're trying to go from a quote-unquote larger thing to a quote-unquote smaller thing, you probably want contraposition. It's always easier to start with the smaller piece and work up to the larger piece than work from the larger piece downwards. So when I see that I want to say something about n squared minus 6n plus 5, I don't really want to start with that. That doesn't sound like fun and something that I can manipulate easily. But if I could just work with n, that sounds like something I can manipulate pretty easily. So I probably want to go contraposition. So let's write down the contraposition first. Contrapositive. So we'd have if n is even, and my pen's starting to freak out, then n squared minus 6n plus 5 is odd. So now we want to try to directly prove this. So, as always, direct proof starts with what do you have, what do you want? let n be an even integer. We want to show n squared minus 6n plus 5 is odd. This is another one that's gonna kind of fall right out. Does anyone want me to do the scratch work first, or can I just start writing it? Raise your hand if you want me to do the scratch work. Okay. So, scratch work. N is even. That's what I can start with. That's the only thing I have to work with. So I know that that's going to be equal to some 2k. Is that a question, or is that you just wanted me to? Okay. I'm going to assume that that was just a please do the scratch work.
Yeah, that
was
all.
All right. So that's all we have to work with. Sorry, Damien, were you trying to say something? I talked over you, but you said you were good, right?
Oh yeah, I was just saying that was that you was
Okay.
correct. That was just move my hand.
Okay, sounds good. All right, so now we want to try to see what the heck happens when we find n squared minus 6n plus 5. That's the only other thing we have to work with right now. So let's see what that turns out to be when we replace things with this 2k. So we have 2k squared minus 6 times 2k plus 5. I guess this one is a bit more in depth. So we're going to have 4k squared minus 12k plus 5. The goal, since I want it to be odd, is 2 times something plus 1. Can I somehow manipulate that to be 2 times something plus 1? First thing I should try to find is the plus 1, because if I can't find the plus 1, then I already know I'm done. But I could break that 5. I could take a 1 out of the 5 and make it 4 plus 1. So now I've got my plus 1. So let me protect it with my life and never touch it again. Now I got to try to manipulate that other piece into some 2 times something. Well, it's got a 4, a 12, and a 4, which are all divisible by 2. So yank a 2 out of it. So if I yank a 2 out of all of that, I'll have a 2k squared minus 6k plus 2 plus 1. That 2k squared minus 6k plus 2 is an integer because just multiplication and addition and subtraction of integers. So we're done. We've got the thing we wanted to go in the box. We have it written as 2 times something plus 1. So now we're good. Questions so far? This is another one of those pieces where I start sounding like it's really simple, and I'm not trying to phrase it as it's simple. It's just what comes out of my mouth. So where are we at? So since n is even, there exists some integer k such that n equals 2k, and then we just redo all that math we just did. So n squared minus 6n plus 5 equals 2k squared minus 6 times 2k plus 5 equals 4k squared minus 12k plus 4 plus 1. I'm kind of breaking it up as I go so that I don't run out of space. Equals 2k squared minus 6 plus k plus 2 plus 1. And once I'm able to write it in that fashion, then we know that that must be odd. So we can say kind of our conclusion for the direct proof piece of it is since 2k squared plus 2, sorry, I'm looking at the wrong one in my notes, and I started writing the wrong thing, minus 6k plus 2 is an integer, n squared minus 6n plus 5 is odd, period. And then the last step with these contrapositions is to just say, since we just proved that, we can now say that the original thing we had, which was the contraposition, is also true. Therefore, I'm going to run out of space. By contraposition, I'm going to start writing on a slope. So therefore, by contraposition, if n squared minus 6n plus 5 is even, then n is odd. And as I've already been saying, so note that the proof by contraposition is a direct proof of the statement's contraposition. Contrapositive. Keep using those words interchangeably. So it's kind of the same thing, just with this tiny extra step of we got to flip-flop it before we prove it, and then flip-flop it back as a last statement. Questions, concerns? I'll let that soak in for a second, because the next piece is contradiction. So if you've got a question on contrapositive, I'll give you another 15 seconds to let me know about it. All righty tighty. This is the last proof idea that we're going to look at. We might not finish all of the examples of this today, but we'll get through at least one of them, which is good. Because then we've done everything. We just might have one or two more examples that I walk through on Tuesday. Proof by contradiction. Some statements may be hard to prove directly, even with contraposition. In these cases, it might be beneficial to try what's called a proof by contradiction. So what you're going to do is to prove that A is true, you're going to start by assuming that not A is true, so otherwise known as A is false. So you're essentially going to say, I want to prove that this is true, but for sake of contradiction, let's say it's not. And what you're then going to do is you're going to work like a normal direct proof until you reach a statement that has to be false. 7 is even would be a very false statement. It has to be something that is 100% absolutely false. And so once you reach something that has to be false, that must have been that your original assumption that A was false was incorrect. So essentially you say, I'm going to assume that this isn't true and then prove that I get out to something stupid, which must mean that it actually was true. So a normal proof sequence, just kidding, this proof sequence, if I'm trying to do a proof by contradiction, essentially what I'm doing is I'm saying let not A be true. We're going to find some steps along the way like we were doing with our direct proofs. And we're going to keep going and keep saying something that follows from that statement beforehand until we get up to something completely false. And essentially the reason that this works is that if we start taking contrapositives of this whole entire thing that I just wrote, if we flip everything, what would happen is we would essentially start with something true. Can I spell? True. That looks really stupid. True. We start with something true and essentially go backwards and negate everything. Essentially flipping everything we did before. But that must have been that we got A and not A. Now, I will say that in these proofs by contradiction, you don't have to rewrite the whole thing backwards. You just say, by contradiction, it must have been true that A was true. So you essentially just have to find this and then just say, by contradiction. You don't have to rewrite the proof in the correct direction. So now it said T and F, but that's because in my notes I only wrote T and F. Sorry. And I actually wrote out the words. So how are we going to go about these proofs by contradiction? So the first thing you're going to do is you're going to assume the hypothesis is false. Hypothesis is true. hypothesis you always assume is true. Sorry. Suppose for the sake of contradiction, and we actually use that wording for the sake of contradiction. I could have very much avoided that. For the sake of contradiction, that the conclusion is false. Sorry, that's the thing you want to assume is false. Hypothesis you always assume is true. We're going to assume that the hypothesis is false and try to get a contradiction. You're going to derive a contradiction. So, well, hold on for a second. Before we look at the next one, though, I have to remind us something from algebra. A real number is rational if it can be written in the form a over b, where a and b are not 0, and they're integers with no common divisors other than 1 or -1. And, well, so a number can be rational and not have that, but we're going to take the fact that you can always reduce a rational number to its simplest form. So that's kind of what this is saying, is that you can always find these two numbers such that you can't simplify it anymore. Like 4 over 8 can simplify to 1/2, but then you'd say the rational number is 1/2. So specifically, as I just said, so that a and b is in simplest form. So that's always something we can do for any rational number. We can find its simplest form. Now, this is a very famous kind of proof by contradiction that we're going to do, and it's the proof that the square root of 2 is irrational. So I wish I could fit more of that in there, but can't, so I'll just leave that. So prove that the square root of 2 is irrational. That is, let r be a real number and prove that if, that should say if r squared equals 2, then r is not rational. So the first thing we want to do is we want to assume that the hypothesis is true. So let r be a real number and assume that r squared equals 2. That's our hypothesis, that r squared equals 2. So we're going to assume that that's true. Next thing is you always say for the sake of contradiction. So for the sake of contradiction. Assume that r is rational. So we want to show that it's not rational, but by the sake of contradiction, we're going to say, suppose it is. And now we have to somehow derive some kind of contradiction from that. Let me make my space for scratch work bigger. So again, at this point, let me come off to the side and do some scratch work to see how I'm going to want to try to make this proof fall out. So I've got that r is a rational, sorry, yeah, no, we're good, sorry. We're assuming that r is rational, right? So if r is rational, we can write it as a over b, which is in simplest form. This is my scratch work, so I might not write all the details out. Like I should say, there exists a and b such that a and b have no, we'll do that in the proof. But so if r is rational, I can write it like that, and I can assume that there are no common factors between a and b. Well, I'm also told that r squared equals 2, which would mean that a over b all squared equals 2. Now this one's going to take a bit of work, and I might need to jump to the next page, but so if I start manipulating that, well, I can square both pieces of that fraction. That's algebraically acceptable. So I'm just messing around trying to figure out if I can manipulate this in some way to start maybe finding a contradiction. Well, let's say, let me swing b squared over to the other side. We might not know what we're doing right away. We're just going to mess around till we find something that might start giving us a contradiction. So that means, as I have it written right there, what would have to be true about a squared then? If I can write it like that, what does that mean a squared is? What type of number? Starts with an E. Even. It's 2 times something. So since I have that a squared is 2 times something, so a squared is even. Now, for proofs that I give you, it won't have to pull on something else you already proved. But in a different example earlier on, example 3, so let me scroll up really super quick. We found out that if the squared is even, then the thing itself is even. So again, for an exam or something, it wouldn't be something that you have to pull from something else. But for this example, we do need to pull that idea. So since a squared is even, by, I think it's example 3, a is even. I will say, as famous as this one is, I would be surprised if any of you could do this from scratch, this specific one. And I say that to try to be encouraging, not to like say y'all are dumb or anything like that. For this one specifically. For some of the other ones we'll look at, you should hopefully be able to follow a bit more. But what the heck am I trying to do here? So I have that a is even. Well, if I started manipulating that around then some more, if I could possibly find that b is even, I'd be golden. Because if they're both even, then they have a common factor. So let me see if there's some way that I'd be able to manipulate this to somehow say that b is even also. Now, I kind of got to jump down here for a second. So a is even. So a equals 2k for some integer k. Since I know it's even, let me start messing around with that a little bit. Well, if I have that a squared equals 2b squared, then I have 2k squared equals 2b squared. Let me scroll down a bit more. So then 4k squared equals 2b squared. Maybe you'll see where I'm going with this. If I divide both sides by 2, 2k squared equals b squared. Why does that make me happy? Because this now means that b is even. Well, b squared is even, which then means b is even. So I've just shown that b squared is even. So b is even. I now have my contradiction. Because what I've just shown in my scratch work is that a is even and b is even, which means they're both divisible by 2, which means they had a common factor. But I said assume they don't. I said assume they're in simplest terms, so they didn't have a common factor. But if they're both even, they have a common factor of 2. So I've just come out to this contradiction, this thing that must be false. Both a and b cannot be even because I said they don't have a common factor. Does that make sense? Of at least why that's a contradiction? Maybe you're still like super howdy. How the heck did you think to get there? So now once we found our contradiction, so we can now go back and start writing the proof. So I'm going to start writing it. And again, this one's hard to see right off the bat. We'll look at one next week which hopefully will be a bit easier to see. Oh yeah, okay, I kind of want to make that into a contradiction by doing this. This one, it might have been a little too many things to work with, and how do you know what you want to get a contradiction as, and blah, 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 blah. Anyway, I'm going to stop rambling and start writing. Where am I? There I am. So the first thing I said, going back to my scratch work, the first thing I did was let R be rational by actually saying what it would be if it's rational. So since R is rational, there are integers A and B with no common factors, with no common factors, such that R equals A over B. And again, I can assume that it has no common factors. A rational number could have common factors, but we can assume that it doesn't. We can assume it's in simplest form. So now we show them all of our kind of math work that we did. So we said, well, then R squared, which is equal to A over B squared, must be equal to 2, because that's by assumption. So then A squared over B squared equals 2. So A squared equals 2B squared. Why haven't I thought to do this before? Let me go back up the tiniest bit. There we go. So A squared is even. And by exercise 3, A is even. Thus, A equals 2K for some integer K. And then we plugged that back in and manipulated it to find our B squared was even as well. So we've got 2K squared equals 2B squared. So 4K squared equals 2B squared. So 2K squared equals B squared. Thus, B squared is even, and B is even. I know this one's a long one. Everyone's like, yes, and I'm tired because it's the end, and just shut up. So A and B are both even. And have a common factor of, no, my God, I'm getting ahead of myself too, of 2. This contradicts the fact that they had no common factors. Thus, I don't want to end this. Yeah. Oh, sorry. not rational. And that's what I mean by you don't have to redo the proof in the other direction. You just say, here's this proof by contradiction. I'm assuming for the sake of contradiction that this thing is false. I do a bunch of work to come down to a contradiction. So therefore, the other thing that I wanted must have been true. Once again, this specific one is a rough one to start with, to be honest. It's hard to see exactly where you were going, but hopefully you kind of at least see what we're kind of going with here, where we want to assume that the thing we want is false and then try to somehow manipulate what we have into something untrue, which would be a contradiction, and therefore we can assume the other thing. So on Tuesday, we'll go through, I think there's two more. Yeah. Two more that we'll look at on Tuesday. Before we start the next chapter, finally. And the next chapter kind of 180s on you. All of a sudden, we're not talking about proofs anymore, we're talking about sets. So maybe people like sets better. I personally love sets. But sets and functions, chapter 2, fun. I'll ask for questions or concerns, but I think at this point people are just done. Okay. What?
The prereq for this class is 133, right?
133.
So this is count, right?
Oh, 122. What is the prereq for this class?
115, 122, 141.
That sounds more like what I was thinking. Qualification through either the mass placement test or a grade of C or greater in any 100 level math course is the prereq for this class. So it's very broad. So I'm making it so that the people online can see the quiz because it wasn't going to pop up for them for another couple minutes, but there we go. Yeah, so a lot of this class assumes a little bit of pre-calc knowledge. If you want, I can try to give you some pre-calc material if you want to try to. Oh, let me take y'all off the big screen people on. It doesn't feel like math. Stop recording.